Cool.
Okay, the next speaker is Justin Kulp from the Perimeter Institute. Will tell us about confinement and holomorphic twists and N=1.
All right. So yes, thank you for having me here. So as was mentioned, I'm going to talk about this confinement and holomorphic twists. And this is based on at least one paper that's out, and then hopefully one that's out soon, and then hopefully one that's out by the end of the year with a whole host of authors, including Matthew Yu, who will be speaking next, and Jingsheng Wu, who's here in the audience. All right, so maybe I should just start because it's 2022 and say why supersymmetry. So SUSY QFTs provide us a rich but tractable collection of theories in which quantities are exactly computable or highly constrained. And this includes things like phases of gauge theories. So some of my favorite things which are tractable or highly constrained in supersymmetric theories come from, like, for example, the non-renormalization theorems, which tells us facts like n=4 is exactly conformal, or in n=2, the beta function is one loop exact. There's also lots of beautiful dualities, which are mostly of electric magnetic duality types. So there's the n=4 Montanon-Olive duality. Then there's sort of a manifestation of this in n=2 theories that goes under the name Seiberg-Witten theory. And then there's forms of Seiberg duality and n=1 theories. So there's also various dualities. And insights from SUSY QFTs can tell us about the real world. And this could be directly, if the real world is supersymmetric, or by studying SUSY breaking. And there was a recent review by Dine and Yu talking about complications and other things to do with obtaining facts about real world QCD from SUSY breaking. Okay, but also it tells us which properties of NF=NC=3 are generic. And for example, in super QCD with NC colors and NF flavors, you can find that there are theories with confinement and chiral symmetry breaking, in particular if NF is equal to NC, but you can also find that there are theories with confinement and no chiral symmetry breaking if the number of flavors is one more than the number of colors. You can also find examples where there are actually just strongly coupled IR CFTs. And then I should also motivate why twists. So the tractability of SUSY QFTs comes, at least in part, from the existence of various protected quantities. And these protected quantities are useful because they can be invariant under deformation of the coupling constant, and also because they can be computable in various duality frames. And this can help us probe non-perturbative physics, especially when there's various strong and weak dualities. So as an example of some protected quantities are F-terms and chiral operators. These are protected by 2 of the 4 supercharges. And they tell us things about the theories because, for example, chiral operators constrain the space of supersymmetric vacua. They're basically equivalence classes of things that have the same VEV in a SUSY vacuum. And F-terms, in some sense, control the deformations of the theories because they're the only things that can be renormalized. There's also objects like the superconformal index, and this counts local operators with signs, but we'll come back to that. And what twisting does is it isolates these protected quantities. Moreover, the twist is completely mathematically rigorous. You can work in BV-BER-ST formalism, and everything you do is completely rigorous. And this is used to success even in mathematics with things like homological mirror symmetry and things like this. So my goal for today is first to explain some properties of the holomorphic twists of SUSY QFTs in general. And then at the end, I'm going to tell you about something that we call holomorphic confinement, which occurs in n=1 super Young-Mills and possibly other places. Okay, so just as a basic primer, supersymmetry enhances the usual Poincare symmetry by adding this anti-commutation relation here. Q's and Q bars turn into momentum. And then the Q's and Q bars anti-commute amongst themselves. Now, given any supersymmetric quantum field theory, we define or perform this holomorphic twist by taking the cohomology of any one nilpotent supercharge. So if we're doing 4D n=1, we might pick Q minus. In this case, Q squared is equal to 0. We have a notion of Q closed operators, and we have a notion of Q exact operators. And then we take this Q cohomology. So in this case, the anti-holomorphic translations are Q exact. So the twisted theory becomes holomorphic, at least cohomologically. Okay, and this is because, as I basically just wrote up here, you see that Q bar produces a translation. And this is the most available and least forgetful twist in that it only needs n=1 supersymmetry. It's also the most realistic in that, it only, again, requires n=1 supersymmetry. And it's also the most challenging because it's not topological, it's holomorphic. Okay, and the operators that are captured by this holomorphic twist, if you're in, for example, a conformal theory, are precisely those that are counted by the superconformal index. So the superconformal index counts, as I mentioned previously, the local operators with signs. And what we're doing here is we're actually going to work with the Q cohomologies themselves. So you can think of the index as basically counting the dimensions of these Q cohomologies, and we're going to actually work with the Q cohomologies. So it's like we're categorifying the superconformal index by working with these holomorphic twists. Okay, so these holomorphic QFTs depend only on the complex structure of the underlying manifold. This is analogous again to if you're familiar with topological quantum field theories. They don't care really about the geometric structure of the underlying manifold at all. They just care about the topology. We only care about the complex structure. Mathematically, the local operators carry the structure of what's known as a holomorphic factorization algebra, and lots of mathematicians like Kevin Costello and others in his sort of orbit have been working on the notion of factorization algebra. And physically, you can think of this, or at least analogously, you can think of this as some sort of generalization of the notion of a chiral algebra or a vertex algebra. For example, in 2D CFT, you have left movers and right movers, and like a holomorphic half or an anti-holomorphic half. And you can somehow think of these holomorphic factorization algebra as being this chiral algebra, but uplifted to higher dimensions. So, and much like this analogy suggests, there's actually beautiful infinite dimensional symmetry enhancements analogous to Virasoro and Katsmoody. And again, much like 2D CFT, these theories are equipped with a local product, which we call the lambda bracket, and its formula is given here. And as well as a series of higher brackets, which describe homotopies between lower brackets. Mathematically, what this means is because we're working with cohomology, you can think of how does this operation, so you could think we're dealing with cohomology, but you could also work at the level of chains. And so you could think of how does, for example, this quantity fail to be holomorphic at the level of chains? Well, that would be captured by a bracket with 3 operators. And then you could ask questions about that at the level of chains, and that would be captured by 4 operators. So that's mathematically what's happening. Physically, what's happening is you can think of what these brackets are going to capture is they're going to capture what happens to a SUSY transformation of O2 when you add an interaction that looks like O1. But we'll come back to that. And I should really stress, this is a statement about the operator product expansion of a subsector of the original physical theory. This is not a deformed or modified theory. So that is to say, like, it is some subsector of the original theory that has, for example, these beautiful infinite dimensional symmetry enhancements analogous to Virasoro or Katsmoody. Now, if I want to obtain the free cohomology in the classical theory, what am I going to do? Well, I'm just going to take polynomials in fields and derivatives, gauge invariant polynomials. Okay, and then the interacting quantum theory can be obtained from this free cohomology by taking yet another cohomology with respect to yet another operator, this bold Q, where each of these Qi's here comes from n-loop Feynman diagrams. This would be like tree level, 1 loop, 2 loop, etc. Okay, and one of the things we find is that in the interacting quantum theory, all the perturbative corrections are contained in those higher brackets I showed you on the previous slide of the free holomorphic factorization algebra. So in particular, this bold Q acting on an operator is given by the sum of all of these creatures here, these brackets, where the tree level term, like I mentioned, is described here. 1 loop involves 2 interactions, and so on and so forth. And if you actually stare at this equation for long enough, I mean, maybe if you cut out these pieces here with the triple and the quadruple bracket, but if you just stare at this piece here, you might recognize this as a Maurer-Cartan equation. And so this is some sort of generalized form of a Maurer-Cartan equation. So somehow what I'm saying is that the free theory knows about its space of perturbative deformations. Okay, so I told you that these things come from Feynman diagrams. So what are the Feynman diagrams in these theories? Well, at least in the 4D n=1 holomorphic twist, they're what are known actually in the literature as Lamin graphs. So here are some pictures of a 1-loop Lamin graph, some 2-loop Lamin graphs, and some 3. Oh, this is a 2-loop. These creatures are all 3-loop Lamin graphs. Now, Lamin graphs have a name, and you might wonder why they have a name. Well, what they are, at least historically, the reasons mathematicians were interested in them, is because they're a minimal set of rigid graphs in the plane. So if you stare at these graphs and you imagine they're all made out of rigid rods, and the vertices are made out of hinges, then clearly if I went and I pushed on the triangle, it wouldn't fall over. But a square, so I mean, I can't believe I'm going to draw a square here because people presumably know what a square is. But You could imagine if this square was made out of rigid rods and hinges, and then I pushed on the square, he would fall over. So the square is not lamin, but the triangle is. So you can see if you kind of pushed on any of these graphs, they would not collapse. So they have no degrees of freedom. And this is actually an important property. And in fact, this notion of lamin graph can be generalized. So for arbitrary holomorphic topological twists in arbitrary dimensions, we find that there's some sort of notion of a generalized lamin graph. And they have some very nice properties. And this is related to work, if people are interested in mathematical work by Confinement or Gautam and Witten, these graphs also appear. Because what actually, it turns out that the type of graphs that show up only depend on the total number of holomorphic plus topological dimensions. So Confinement, in studying Poisson deformations, he was interested in topological twists of 2D theories. So he had two, and we're interested, we're interested in two holomorphic directions, and he was interested in two topological directions. So the same graphs actually appeared. Anyway, we can go into more detail about that afterwards. Now, an arbitrary integral, remember we're studying Feynman diagrams here. An arbitrary integral takes this spooky form here. Now, we don't have to go into the details, but you can tell it looks like a long and intimidating formula. But if you stare at it for long enough, you find that a particular change of variables maps this integral to actually just a simple Fourier transform of a polytope in loop momenta. So you change the scariness here into some sort of complicated polytope in the space of loop momenta here. And we call this polytope the operatope. We find that the Feynman integrals then satisfy an infinite collection of quadratic identities coming from this operatope here, which roughly speaking enforces the associativity of these brackets, which I showed you on the previous page. And using this, we actually find furthermore that you can bootstrap all the Feynman integrals in these theories from these identities. So we compute, for example, this one loop Feynman diagram by hand. And then there's some quadratic identities that involve the one loop Feynman diagrams and the two loop Feynman diagrams and relate them and tell you that like some complicated sum of them with derivatives acting on them is equal to 0. And then from that, we can just read off the two loop Feynman diagram answer. And we also do it for three loop, etc. So we're at a conference on confinement, and you may be wondering, besides applications to, SUSY QFTs, what does this have to do with confinement? Well, it's if we start a particular example, let's say n equals 1 super Yang-Mills. This is an SUN gauge theory with an adjoint fermion whose Lagrangian looks like this. And we can perform the twist of it, and I'm not going to go through the details, but you can take the twist. And then you find, or at least mathematicians will tell you, like with a rigorous theorem, that you can identify it in some non-trivial way with a holomorphic BC system. Okay, the fields in this holomorphic BC system are collected in an adjoint bosonic superfield B and some coadjoint fermionic superfield C. They have two components. It's like a little bit complicated, right? Like C has the C ghost, and then it also has like the anti-holomorphic gauge field, and the B's got like the holomorphic piece of the field strength, etc. But anyway, the Lagrangian of this theory looks like this. Okay, and based on time, right? So the free cohomology is just going to be something like this. Remember, I told you that the free cohomology is just going to be gauge invariant, like words in things that are made out of the fields and their derivatives. So it's just going to be something like this. And let's see, what's one quantity in it? Well, one quantity in it is the stress tensor of this theory. So the stress tensor of this theory comes from the stress tensor of the mother untwisted theory. That might be S alpha. And you can see that, for example, the derivative of the stress tensor lives inside this cohomology. But what we find at the free cohomology, but what we find is that if you add one loop corrections, then this derivative of the stress tensor actually becomes Q exact. Now, the derivative of this stress tensor in this BC system generates, among other things, all the remaining space-time symmetries. Well, it generates these things called Hamiltonian symplectomorphisms, but really amongst those things are all the remaining space-time symmetries. And so if this quantity is exact, then that means local operators are invariant under the remaining space-time transformations, much the same way that if you, that the way that the anti-holomorphic translations were Q exact, it meant correlation functions didn't depend on anti-holomorphic coordinates. So since all the remaining space-time symmetries were generated by this creature here, and it's now Q exact, we actually find that the theory becomes topological once you include one loop corrections. So we thought we were going to study a holomorphic theory. And then when we actually add the quantum corrections, that the theory becomes topological at one loop. And so being topological is compatible with confinement, because if it's topological in the UV, and is topological in the IR. And indeed, we know that supersymmetric Yang-Mills confines, and so should probably be, well, it's confinement at it's topological at long distances. And so we get some sort of commuting diagram, if you will, that looks like this. And we also get constraints on the IR physics, because the holomorphic twist of whatever IR theory you have, anywhere along the flow, must also be topological. And so we call this phenomena here holomorphic confinement. And we also study some large N calculations, and they have interpretations with a twisted holography dual, but I don't think there's time to go into that, so let me summarize. So in conclusion, SUSY QFTs are toy models for real-world physics, and their tractability comes from various protected quantities, which we can isolate with twists. And these have very much beautiful properties like infinite dimensional symmetry enhancements, Feynman diagrams, which appear to be completely bootstrappable, and possibly a novel UV manifestation of confinement. And so some future goals include things like we could study super QCD. This twist has some analog of a 4D Kac-Moody symmetry. We might want to study Seiberg duality, so we could actually perhaps prove Seiberg duality at the level of cohomology. And this will require various non-perturbative corrections. And another fun project would be to study n equals 4 super Yang-Mills, because then we could compute the cohomology of 1/16 BPS states, which correspond to black holes. And one final point is, because we have these infinite dimensional symmetry enhancements, somebody should really work out the representation theory and the character theory of these things, because it'd be very interesting to know if things like the superconformal index could be written as just like a finite sum of characters or something like that. So I'll conclude there. Thank you for listening.
Thanks for an excellent talk. Just a very quick question. So you said that this twisted theory is a subset. It's just a set of operators in the original theory.
Right.
Can you say briefly what these operators are from the n-equal 1 super Yang-Mills?
Right. So I mean, we're basically collecting the things which are killed by one supercharge. So that's basically the statement of what they are. But if you want to go and use one of these mathematical theorems that like relates them to the B's and C's, the identification of various quantities is not always like 100% obvious. But yeah, that's what it's isolating.
Matthias.
So if you do this for n equals to 2 theories, would you get something similar to this Bastelli, beam, etc. algebra?
Right. So there's the n equals 2, 40 n equals 2 theories. There's these vertex operator algebras that Beam and Rastelli have found, and other people, and those have had input for the bootstrap. So if you study a 40 n equals 2 theory, you have our infinite dimensional symmetry algebras, and you actually do a deformation on those to obtain the ones that are in the Beam-Rastelli paper. So in some sense, I think this information is actually richer than what goes into the 40 n equals 2 calculations, and it would be very interesting to know if you could use them somehow for the bootstrap.
Can I also ask a question?
The relation with the superconformal index, because I thought that needs a UNR symmetry. Well, you don't have UNR symmetries. Right.
We're not putting it on. So we're not putting it on S1 times S3. We're just doing calculations on C squared. So we're not like spoiling the U1R symmetry or anything. Like so it doesn't matter if there's a U1R, like it doesn't matter if our U1R symmetry is spoiled by like one loop corrections, I guess.
It's not related to the usual superconformal index like on a sphere. It's related to some flat space generalization. Yeah,
we're computing cohomologies in flat space. I mean that's the one thing we're definitely doing. Sorry.
In the case where there's a conformal field theory in the infrared, is it possible to compute correlation functions of some of these operators in the CFT?
So we haven't actually computed any correlation functions. We've mostly just been counting things, but I guess in principle,
Like you said, it seemed that OPs is something you can compute, but not necessarily.
Yeah. Right. It sounds like in principle, but again, that's not something we've done.
So it's the question about your last point about this enhanced topological symmetry.
Yes.
The fact that it happens at one loop, it sounds a little bit surprising because indeed, if the loop expansion has an expansion parameter,
yes,
isn't your thing on the right hand side? That is, how does that work? Normally, if you have quantum corrections, you lose symmetry, you don't gain symmetry. So is there in your expansion parameter a 1 over your expansion parameter in front of your trace.
I mean, yeah, right. So the expansion parameter is just loops. It's just H bar. But yeah, I don't know. It's very surprising. I guess I don't have any.
Yeah, at least I don't know what the other example was.
Right, and I should also add too. I mean, it's this thing. I say it happens when you add one loop corrections, but higher loop corrections also don't spoil it. So yeah.
We had one question on Zoom, right?
Maybe no, somebody was trying to speak on Zoom.
Any questions from the?
Hello, Zoom.
So I have a question about this notion of holomorphic confinement. If the theory deconfined, wouldn't you also say you get a topological theory in the infrared? Like, in which senses are you getting anything about confinement here?
Yeah, I mean, it's okay. So the short answer is I don't know, because we actually do, I guess, need to better understand what the relationship is of this so-called holomorphic confinement, the statement that the twist becomes topological to actual confinement. So perhaps what I should say is we have a conjectural novel UV manifestation of confinement. But yeah.
Okay, let's thank Justin again.